Hello, everyone. So first off, we have no disclosures. Okay. So pancreaticoduodenectomy remains a highly morbid operation. Outcomes are with a mortality of about 1% and an overall complication rate of 20 to 65% in most series. Morbidity is primarily driven by the three anastomoses and the pancreaticojejunostomy and consequent post-op pancreatic fistula contribute the lion's share of morbidity. Minimally invasive surgery affords multiple benefits, and these are both for the patient and for the surgeon. For the patient, we have shorter length of stay and reduced complication rates in some series, and for the surgeon, there's 540 degrees of movement with the wristed instruments, which is really useful for the complex intracorporeal reconstruction portion. And also the 3D high-def imaging helps a great deal during the operation. Can we go back? Okay. A side effect of minimally invasive surgery is that we can record video, and therefore we can review video, and this helped us do a large body of research that linked surgeon technical performance intraoperatively to lower rates of complications, and this has been seen in bariatric surgery, in colorectal surgery, and in pancreaticoduodenectomy. However, there are practical limitations to this kind of research, mainly that for example, for our paper from Pitt, we required a trained HPB surgeon, and this was expensive and time-consuming, as you can imagine. And there were still difficulties with the inter-rater correlation. We tried crowdsourcing, but crowdsourcing was also fraught with some difficulties. And so deep learning addresses these limitations. It's cheap and inexpensive. It eliminates, I wouldn't say eliminate, it reduces human error, and it allows for the automation of segmentation, grading, and outcome prediction. And so in this work, we aim to utilize deep learning algorithms to automatically segment pancreaticojejunostomy videos from robotic pancreaticoduodenectomy. This is a retrospective review of a prospectively collected video database of RPDs at a tertiary referral center. We segmented the Whipple into resection and reconstruction phases, as we'll see shortly. And the pancreaticojejunostomy was annotated into specific tasks using internal labeling software that we developed. This is the general steps for the pancreaticoduodenectomy. This is the resection phase. That is the reconstruction phase. Within the reconstruction phase, the PJ constitutes one of the steps. The PJ itself is then broken down into different tasks. So the posterior mattress, the ductal mucosa portion, and the anterior buttress sutures. And these are in turn divided into the first through third mattress suture. Sometimes there's a fourth, the posterior duct and anterior duct sutures, and the first through third buttress sutures typically. These are representative images of the specific steps. This is the posterior mattress suture, here's our ductal mucosa suture, and here's the anterior buttress suture. This is our internal labeling software. The pane on the left allows us to annotate the start and end of a specific task. The pane on the right is part of an additional project on doing task-specific grading for the PJ. And so we used a deep convolutional network, a neural network model. We had a training set of 40 videos and a validation set of 16. The model itself looks at specific image features and tries to predict which step this image belongs to. We also added frame level classification to that to improve its output and reduce noise, as we'll see later. So the first row constitutes the ground truth, or our annotations of the video. The second row constitutes from the convolutional neural network model, which you can see there's a lot of segmentation, a lot of noise, and this happens a lot because a lot of the steps are kind of repetitive with suturing tasks and stuff like that. Whereas when you add time, which means the number that the frame is supposed to appear in, you reduce a lot of the noise and end up with an accuracy level of 70%. These are the specific tasks that we ended up annotating. The model performed best for tasks that were unique. And the superior mattress stitch, the enterotomy, the posterior ductal mucosa stitch, and the anterior ductal mucosa stitch had the best performance. This is a busy diagram, but really what you want to look at is the diagonal in the middle. So the bottom represents, the x-axis represents the actual deep learning model. The y-axis represents the ground truth, which is our annotations. And you want to look at the diagonal. The diagonal, the warmer it is, that means our model is performing better. And it just represents what we saw earlier, was that the best performing models were the ones that had the most unique features. So the superior mattress suture, the enterotomy, the anterior ductal mucosa, and the posterior ductal mucosa and the anterior ductal mucosa. Now, our study has several limitations. So first off, the data is from a single site, and so may suffer from selection bias. Additionally, we need much more video, and we're in the process and have already annotated over 100 pancreaticojejunostomy videos. Our deep learning model uses image classification, but we're looking at video, and that is a big limitation. So we're trying to work on using a 3D CNN type model to classify the videos directly, and that will improve that will reduce our noise, so to speak. So in summary, task analysis using CNN and frame level classification allowed for automatic segmentation of pancreaticojejunostomy videos with reasonable accuracy. And in conclusion, video analysis using deep learning algorithms can automatically segment surgical video of robotic pancreaticoduodenectomy. The next steps, which is what's really important, is utilizing deep learning models to automatically grade and predict outcomes. So you can get, so in a perfect world, you would get instantaneous feedback as you're operating. Thank you, and I will take any questions.